CS61C, Discussion 13. Question 2, Coherency and Atomics. The benefits of multi-threading programming come only after you understand concurrency. Here are two of the most common concurrency issues. One is cache incoherence. Each hardware thread has its own cache, which means that data that's modified in one thread may not necessarily show up as updated in the other. This can often be solved by just bypassing the cache and writing directly to memory, such as using volatile keywords that are present in many programming languages. Number two is read, modify, write. Read, modify, write is a very common pattern in programming. But in the context of multi-threading programming, interleaving or layering of read, modify, write stages often produces a lot of issues. Essentially, the order of these stages is extremely important, especially the order of the stages between multiple threads. In order to solve the problems created by read, modify, write, we have to rely on the idea of uninterrupted execution, also known as atomic execution. In RISC-V, we have two categories of atomic instructions. One is load, reserve, store conditional, which allows us to have uninterrupted execution across multiple instructions. The other is ammo.swap, which allows for uninterrupted memory operations within single instruction. Both of these can be used to achieve atomic primitives. Here are examples for each. We'll be going more in depth with these examples as we explore the concepts surrounding them. On the left, you can see ammo.swap being used as ammoswap.w.aq and ammoswap.w.rl as individual instructions. And on the right, we can see load, reserve, and store conditional being used as lr.w and sc.w. Now we'll be going over some instruction definitions. Load reserve, or LR, loads the 4 bytes at the memory address located in the first argument register, or RS1, then writes them to RD, the destination register. It sends the result, if necessary, and registers a reservation on that word in memory. Store conditional stores the 4 bytes in register RS2, the second argument register, to the memory address stored in RS1, the first argument register, provided there exists a load reservation on that memory address. It writes a 0 to RD, the destination register, if the store succeeded, or a non-zero error code otherwise. Ammoswap atomically puts the signed extended word located at the memory address stored in RS1, the first argument register, into the destination register, then puts what is stored in the second argument register at the memory address in the first argument register. Now we'll go over the methodologies that we saw in the examples. The first is test and set. We have a lock stored at the address specified by A0. We utilize ammoswap to put in a 1 at that address and get the old value. If the old value is a 1, we would not have changed the value of the lock, and we will realize that someone currently has the lock. But if the old value was a 0, we will have just locked that lock. And we can continue with the critical section, which is the part of the code we want to execute without interference. When we are done, we will put a 0 back into the lock in order to unlock it. The other methodology is compare and swap. Compare and swap tries to first reserve the memory and gets the value stored, then compares it to the expected value. If the expected value and the value that was stored do not match, the entire process fails and we must restart to update based on the new information. Otherwise, we register a reservation on the memory and try to store the new value. If the exit code is non-zero, something went wrong with the store and we must retry the entire load, reserve, and store conditional process. Otherwise, with the 0 exit code, we continue into the critical section, then release the lock, similar to test and set. Now, let's go over the two examples in more detail. On the left, we have test and set. First, we set T0 to be 1. In this case, 1 means locked and 0 means unlocked. Then we use the ammoswap instruction to set the value at the memory address stored in A0 to be the same as the value in T0, which is 1. And then we take the original value that was stored at that address and put into T1. Then we compare the original value with 0. If they are not equal, then we have to go back to the start label and do all of this again. But if they are equal, then we know we've effectively locked, and we can go through with the critical section. Finally, we do ammo swap in order to set the value at the address in A0 back to 0, and we discard the 1 that was there originally. On the right, we have compare and swap. Here, A0 starts as holding the address of the memory location we want to work with. A1 holds our expected value, and A2 holds our desired value. At the end, A0 holds the return value or the exit code. It will be 0 if we have a success, and it will be non-zero otherwise. Let's start at the CAS label. First, we do a load reserve in order to retrieve the value that's at the memory address in A0 and put into T0. And we attempt to place a reservation on that word. Then we compare the value against our expected value. If they don't match, then we failed. So that means we have to go to the fail label, load a 1 into A0 as our exit code, and return. If they are equal, then we can store conditional, or at least attempt to. We take our desired value and try to put it into our reserve memory, which is at the address stored in A0. Then we set A0 to be the exit code corresponding to whether or not the store succeeds. And then we return. Now let's go over question 2.1. Why do we need special instructions for these operations? Why can't we just use normal load and store for load reserve and store conditional? And why can't we expand ammo swap to a normal load and store? For load reserve and store conditional, after the load reserve, other threads cannot write to the location marked reserved. Hence, the value loaded from memory will be unchanged between load reserve and store conditional, which cannot be achieved with a normal load and store. Store conditional is also dependent on the memory being reserved, so we cannot just replace it with the regular store. For ammo swap, it does load and store with one single CPU cycle. Hence, the operation is atomic and uninterruptible. This is obviously not achievable with two instructions, which would be load and store individually. Question 2.2. Now that we have atomic operations, let's try to experiment with them. Let us try to implement an algorithm that enforces ordered thread execution. This means that if we have 4 threads, thread 0 goes first, thread 1 goes next, and so on. For this problem, assume that A1 holds the location of a piece of memory we have access to for the entire duration of our algorithm. Note that this does not mean that this memory is reserved, just that we have access to it. Also, we can assume that there exists a label getThreadNum that returns a thread's number in A0, and that we save RA to the stack before line 1 and restore RA immediately before line 21. Try to fill in the blanks below. Please use load reserve and store conditional for this problem. Let's go over our starter code. First, we set T0 to the value of 0. Then we have a line that should do some setup for the first thread, or thread 0. Then we have a placeholder for the code that would spawn our threads. Then, starting at the check label, we have a JAL instruction that should get the current thread number. Then we have to get the ID of the next thread that should operate, and we should make sure that this cannot be interfered with. After that, we probably have to insert some more code before we get to incrementing T0 by 1 at the done label. Then we set which thread is next to run, and then we have a branch instruction. And then we have a placeholder for some code that should join whatever thread we're on back with the other threads, and then we return. So to start, we immediately can fill out the JAL line. We know that it's intended to get the current thread number, and we know from the instructions that we have a label, getThreadNum, that will retrieve for us the current thread's number. So we can just do this. Now, looking at how T0 is being modified, we first set it to be 0, which is the value that corresponds to the first thread. And then at the done label, we increment it. By putting these together, we can presume that T0 probably has something to do with whatever thread number. It gets set to 0 as the first thread, and when we increment it, it probably indicates that we should be moving on to the next thread based on the fact that the label next to it says done. However, T0 might be changed when we get to get thread num, so we should probably save it. And luckily, we have a piece of memory where we can save it. Its address is placed in A1. So we can just do a normal save word of T0 at the address stored in A1. Next, we want to get the ID of the next thread that should operate. So the first time through, it should be 0, which is currently stored at A1. We also want to make sure that this cannot be interfered with. So we can look to our load reserve instruction. This in particular does two things. It restores T0 in case get thread num perhaps changed it. And also, it reserves the spot in memory pointed to by A1 so that there's no interference. Now that we have the expected thread number back in T0, we should probably check our current thread number, which is stored in A0 thanks to get thread num, against it in order to make sure that we want to proceed. If we do not have those line up, then we probably want to start again instead of trying to proceed. So we can do something like this. This branch not equal instruction will go back to check, which basically means check the thread number again, and then check the ID again if our current thread is not the thread that's supposed to be going. If it is, then we can go to the done label, increment T0 by 1, and then set whichever thread is next to run, which means that we want to save our new T0 value back into A1, which we can do using our save conditional instruction. Here we save this new incremented value of T0 at the spot in memory pointed to by A1, and we get our error code or our success code. Our success code being 0, our error code being a non-zero value. This tells us whether the store conditional was successful or not. If it wasn't successful, then something has gone wrong and we need to start this whole process again. So looking at this branch not equal instruction, we can fill it out like this. If our return code is not equal to 0, then we should go back to the check label. Otherwise, we're done. We can join our current thread with our other threads and then return.